All right, in the second video, we got a kind of a strange situation. There's a collar and it can slide, but it's attached to a spring. Now, the initial condition has the spring up here like this, and then the collar is here, and that initial speed is 2. Okay, and in the end, the collar gets all the way down here to B, and so that spring is stretched out sort of like this. Okay, and what we're trying to find here is the speed at B. So that's what we want. V final is something. That's what we're after there. Okay. All right, so we're just going to set this up with energy stuff. So the first thing I'm going to do is just sort of write down my equation. Kind of at this point, I don't really know necessarily what am I going to have to figure out, what am I not going to have to figure out. But once I write that equation down, start moving forward, then I'll be like, oh, I need this value, I need this value. Okay, and then I can work them out, like that. So let's come up here and it's got our delta K minus delta U, just like this. And so we'll have a half M V final squared minus V initial squared. Okay. It's kind of nice in the last problem where that term was just 0. Okay, and then we've got some gravity to contend with here. So let's put that in there. So we've got minus mg delta H. All right, and then my spring effect, so minus a half K S final squared minus S initial squared, just like so. Okay. So now let's see what we got to figure out in there. All right. So we've been told the value of the initial speed. Okay. So we have that right there. We need the height change. Okay. So let's see if we can figure that out. So we're up here and we're coming all the way down to here. All right. And it tells us that this arc is a portion of a circle with the radius of 0.4. And so that means our delta H is actually negative 0.4. Okay, so, okay, great, we got that. Piece of cake. K, we know the spring constant. They tell us K, it's 400 right there. And then what we need is SF final and S initial. Okay, so now remember, these numbers over here, they're the compression values, not the actual length of the spring. All right, so what we have at the top at position A, the length of the spring is actually 0.1. However, the resting length is 0.2. So that means S initial is compressed. Since it's compressed, I'll call that negative. It's compressed minus 0.1. Okay, and then this distance at the end, right here, let's look at that. So I've got a triangle here, 0.3, 0.4. I know that's 0.3 because the whole thing is 0.4. So we just back off 0.1 and that leaves us with 0.3. So that whole length there is 0.5. So S final is we subtract off the 0.2 and we're going to get 0.3. Now, so I made the one term negative because it's a compression and the other term positive because it's a stretch. Okay. Now look at this. Is this weird? Does this seem weird to you? Okay, if I put my positive number in there, that's fine. If I put my negative number in there, that's going to turn out to be a positive number. Huh. All right. But if it's just a positive number, how do I know if it's not compressed or stretched? How am I going to know that? Okay, well, let's think about it this way. Somewhere, all right, let me get a new color here. Let's zoom in on this thing here. Somewhere, okay, maybe right here, it looks like the spring is uncompressed. All right. But just a little bit further than that, the spring has stretched out. And it might be stretched out to a distance of 0.1. So that I started out with negative 0.1 and I ended up with positive 0.1. Okay, so what's my spring change energy from one side to the other? Well, it's 0. Okay, because they're squared. They're squared. And what that really means is when the spring is compressed, it's pushing out, and that's going to try to accelerate it, right? That's going to make the little collar piece go faster. But once it passes equilibrium at point C, now the spring starts to slow it down. So at the exact point, of course, gravity is going to screw this up, but just in terms of our spring energy, okay, if we didn't have any gravity, then our velocity here would be exactly the same as we started. Now, it won't be because of gravity, but if we could turn gravity off, that's the situation we would have. Okay, and if we could turn gravity off, this thing would go like wah, 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 or something like that. Okay. Okay, so the bottom line is whether it's a compression a certain amount or a stretch a certain amount doesn't really matter. Okay, so in this thing, the compression to the stretch from minus 0.1 to plus 0.1 is sort of like cancels itself out. And all that really matters as far as the spring goes is what happens the rest of this way right here. Okay, that's all that really matters right there. So that's, one of the beauties of this thing being a squared term is that's how it's going to work out for us. All right, now let's go ahead and get some numbers in here. Well, we're going to do a little bit more algebra. I'm going to take my 1/2 m over to the other side. Okay, so that's going to, and then I'm going to put my v initial over to the other side as well. So I'm going to have v final squared is going to be v initial squared. Okay, minus 2g delta h, okay, minus k over m, s final squared minus s initial squared. Okay, just like that. Now we'll put in some numbers on this thing. So my initial speed was 2 meters per second, I think. Yeah. So I've got 2 meters per second squared minus 2, 9.81 meters per second squared. H is minus 0.4 meters. Okay. And then my K is 400 newtons per meter divided by my mass, which I've forgotten, 4K. And then SF we said was 0.3 meters squared minus 0.1 meters squared. Okay. There we go. Let's take a look at our units real quick. Okay. The first term, meter squared over second squared. Great. Second term, meter over second squared. That's the same thing. Works out. Okay, then down here, I've got Newton meter per kilogram, meter squared, and meter squared. Ugh. Okay. Well, that's kind of nice. I got my meter squared here. If I can get the rest of this to turn into 1 over second squared, I'm in good shape. So a Newton is a kilogram meter per second squared. Oh, that's good. But it's a Newton per meter. Oh, nice. So my meters are going to go away. And it's per kilogram. So I got a kilogram down here. So that's going to go away. Ah, there we go. Now I got my meters squared on top and my second squared on the bottom. So it's going to work out just fine. Okay. And anyway, so VF squared turns out to be 3.848 meters squared per second squared. And that means my final velocity, take the square root of that, 1.96 meters per second. Okay, ta-da! Okay, now that's the end of that one, but I want to do another thing in this one that doesn't have anything to do with this problem, but it shows up in another problem. So don't stop the video just yet. Okay. And that is, I'm interested in, and I got to do some erasing. I want to know what's the normal force at B. Once we get all the way down there to B, what's happening with my forces on the pole? Okay, so let's come down here, draw this guy in. Okay, there we go. Take a look at our forces. All right, so there's going to be some normal force from the pole. And so let's say it's this way. And I'm going to say that, I'm going to guess that because my centripetal acceleration is towards the center. Okay, so I'm just going to say, well, let's suppose that's going that way. All right, then the spring force is straight back like this, Fs. Okay, and then there's also the weight acting on it. Okay, so let's do a free body diagram while we're doing this here. Whoops, let's go a little further. And I'm not happy with that. Well, I'm not real happy with that either, but we'll live. Okay, so here is our normal force. Now, then what I'm going to do is I'm going to split this, go ahead and split it into F spring X and F spring Y. And then here's my weight, mg. Okay, and just to help me remember, I'm going to write down my centripetal acceleration term there. Okay, so that's going to help me make sure I keep my signs straight, positives, negatives, and all that sort of thing. Okay, so that's a little small there. We will work with it. Okay, so let's look at our forces. What's happening vertically, we don't care because, specifically I said I'm interested in the normal force. I want to know what the normal force is. So we're not going to worry about the vertical information. So we're going to go straight for our radial content, F sub r, and that's going to be MAC. Okay, so we've done this many times now. So I'm going to have minus N minus F spring X, and that's going to be MAC, which is going to be minus M V squared over R. All right, there we go. Oh, look, okay, so everything's to the left. All right, now we could have done that. I mean, we could have done that to begin with. We could have said, well, let's call this positive, and then it'd be fine. Okay, but I just decided not to do that. So now I got to rewrite it all. Equals M V squared over R. There we go. Okay, so I want to find N. Okay, so N is mv squared over R minus the force of the spring in the X direction. Okay, so let's talk about that term. So Fs is just going to be K, in this case, S final. Okay, so how far it's stretched. But what we need is the X component. Now remember that it's sitting on a 3, 4, 5 triangle. So if we come up here and we do that, we've got 3, 4, and 5. So that means my X component is going to go as 4/5, and my Y component would go as 3/5. Okay. So Fsx is 4/5 of K SF. All right. So let's go ahead and work with this a little bit more. N mv squared over R minus 4/5 of K SF. Let's throw some numbers in there. My mass was 4 kilograms. My velocity squared term, okay, I had that. My velocity squared term was 3.848 meters squared over second squared. And then divided by r, which was 0.4. Okay, so there's my mv squared over r term. So now I got to do my x component of my spring. So minus 4/5 by 400 by 0.3. Okay, there we go. All right, there we go. Now, let's plug in all those numbers there. Okay, and let me copy this over from my future work. I got 557.52 newtons, except it's actually negative. Just like that. Ooh, what do we do with that? Well, if you remember, we've seen this kind of thing before. If we end up with a negative number on our force, it just means we guessed wrong. Okay, so the actual direction for the normal force is this way. Okay, so even though it's on a curve, heading down, the spring force is so strong, okay, it's more than adequate to provide the necessary centripetal acceleration. So the normal force is kind of actually holding everything back, all right, in a sense, in order to help us make the curve in a nice arc instead of a parabola or something goofy. Okay, so now I do that because one of your other homework problems has something like that, where you're going to have to find a normal force that's involved. And so, wow, boy, that is tiny. Anyway, this is how you're going to have to do that, okay? You're going to have to come in and figure out what's your velocity term. And once you've got that, then you can come back to your other information and set your equation up however you need to in order to get that normal force. Okay, so just kind of follow this example once you get to that. All right, so most of these are pretty straightforward, but you will have to bring in some other information, okay, about what's happening with forces, kind of like what we've done here. All right, there we go.